Hello, everybody, and welcome to just another quick help session. So I've done one previously in energy efficiency, and I'm doing this one as a result of some results and feedback and so on that I'm getting through the process of marking some of the assignments. So yes, Michael Jenkins here, and a couple of things I've noticed in some of the assignments is, well, the commonality of the issues that people are having centers around two aspects. One of them is working out the appropriate eaves width for windows and adequate shading. So I'll go through a fairly simple example of that and the processes and the inputs involved for that, basically to directly apply to that assignment for the some of you that would like a little bit of additional input in regards to that. And another one I've noticed is in the gizmos section that the majority of people are selecting a reverse cycle or a split system air conditioner, but specifying the kilowatts of output as opposed to the input energy required to run that system. So I'll go through both of those. So first up is the section on Windows. To complete that, the section on task number 4, or question number 4 in task 3, sorry. We'll start off, I think I'll draw your attention to an excellent resource, which is the Your Home Guide. So obviously there are the recordings here, but there's also the Your Home Guide. So click on that, and it's getting there. So here we go. So Your Home, and that's linked specifically to glazing, and there's plenty of excellent information here in terms of glazing. So U value, SHGC, etc. What's appropriate for what sort of orientation? Excellent info, but that's not directly related to what we'll be looking at today. What we will be looking at is the shading component. So if we head back up to here, click on shading, that takes us to a section which is a fantastic rundown of the basic concept of passive solar design and what's really required to provide adequate shading to windows. I'll cut to the chase, or I'll scroll to the chase basically, and get us right down to this diagram here, where it shows adequate shading to northern windows for latitudes south and including 27.5 degrees, so south of the tropic. So that means 27.5 degrees, that's Brisbane basically, and so that includes us. Now this is a very much a rule of thumb. So as an initial guide or initial idea, you can use this to work out a distance of H, which is from the sill of the window to the underside of the eave, and then your eaves overhang should be 45% of that distance of H. So that's a really good rule of thumb. And another good rule of thumb is that your window head height should be 30% of the distance of H. So that will give you a pretty close reading as to what's the most appropriate eaves overhang for a due north facing window. But there are also excuse me, also other ways of getting that a little bit more accurate as well. So if I flick over here, that's interesting. We've got, that's opened up fully, that's good. Okay, so if I flick over here to our question 4, we're asked for determining what the correct eaves width. So select appropriate glass type for location windows. Refer back to the Your Home Guide for that one. But in section B here, calculate minimum eaves width required to protect glass, and then indicate with dimensions floor exposure for winter solstice and summer solstice. So we have this building here in Victoria Square in the city. For the purposes of keeping this simple, assume this face of the building is facing true north. We've got a bit of a funny north arrow happening there, but we don't actually have any dimension in the degrees of offset to north. So for the purposes of this, treat that as due north. Then over here in our glazing schedule, we get a little bit of an idea of what our window head height and our sill height is, because we can work backwards from this. So we get our window head height of 2100. Then we've got window G1, a sliding window that is 1800 high. So that gives us an idea then of our eventual sill height that we can work with. And we've got window G1, G2, G3, G4. Window G2 is a far lower window, but also in the purposes of determining what our adequate shading is, it's G2. We can disregard G2 for the purposes of keeping this fairly simple, because it's a bathroom. So it's not actually a habitable room that we're determining our shading for. So the priority goes to determining that shading for G1, G3, and G4, which 1800 high, 1800 high, 1800 high. So how do we do that? So by and large, the majority of you have worked that out and worked that out fairly well, employing various different methods, but basically having the same inputs. And those inputs primarily come from this application called Sun Calculator. So it's taking a little while to open. So what I will do, oh, here we go. So it's open now. So that's located on the Learn page. Actually, I will show you exactly where that's located on the Learn page. So we've got your home guide here. But if we scroll right down, we've got this Sun Calculator here. So also there's the instructional video from Merrin using Revit. It's going to show you basically the same sort of things I'm showing you now today, but I'll go into a little bit more detail there than that one. So we've got Sun Calculator, and so you've clicked on that, and we've got our Sun Calculator. Now, what we're primarily concerned with protection of windows is our summer solstice and getting our height for height of the sun at summer solstice. So we can here it's set to today's date, showing us the angle of the sun. We can change that date to summer solstice and or winter solstice for getting that height of the sun. So I won't actually give the game away entirely and tell you which day is summer solstice, which is winter solstice. I'll leave that one to you to determine, but I'll show you just how to use this Sun Calculator just to tweak it a little bit. So what we've got up here, we've got a sliding bar that moves our sun around. So what we can do, we can move our sun around. Meanwhile, we look at our altitude of the sun. So that's what we're concerned with. So the azimuth is our angle of the sun in this direction. Our altitude is how that sunlight will be hitting our windows. So what I'm looking for is, for summer solstice, I'm looking for that steepest altitude, which is got to be not quite at midday. It'll be a little bit past midday. So we've got altitude of 46.94. That's so that's the highest altitude I can get, 46.94, and I'm at 13 minutes past 12 during the day. So I've used this little sliding bar at the top to find my highest altitude, and then of course you'll do that for winter solstice and summer solstice. Then once we get those angles, by and large the easiest way to do that is then draw things up in a drawing program. But if you don't have a drawing program, you can actually do this by hand as well, drawing everything to scale. But there's also the possibility of using trigonometry and determining angles from trigonometry. I won't go through that today, because by and large, the bulk of you are able to muck around with the drawing program of some sort. And for those that can't muck around with the drawing program, can work through it manually, which will get you quite an accurate result as well. So we've worked out our sun angles for that height of the day in summer and winter solstice, with the assumption that our wall is facing due north. We've also worked out what our window head height is, and let's say, so this is a completely different building, by the way. We have a far steeper pitch on the roof. We have far higher floor to ceiling. We've actually got 2400 window head height on this one. But let's say we had an 1800 window, so I'll go 100, and I'll set our sill height down there. So from our 2400 with an 1800 window, we end up sitting at 600 mil above the floor. So then I'll get my here's some lines I've already drawn, ready for that, and I'll rotate those to the right sort of angle. So let's go. So that's given you 75 degrees. Now that's not actually the exact angle that you'll get. So sort of round about there for summertime, but it's but I won't give the game away entirely. Let's say it was at 75 degrees. What I can do is I can move a line in the drawing program to intersect with and I didn't quite grab it the right spot, so I'll just move it again. Make sure we're being quite accurate. And that puts my summer sun hitting right on the edge of my glass at my sill height, for example. I follow that up, and then what I end up getting is this. So this is a building which we can drawn up previously in section there, and I get an intersection between the eaves line and that summer sun angle. I can measure that distance, or I could dimension it either way. Measure that distance back to our wall. Back to the wall is fine. You could do that back to the timber framing if you so desire, but back to the wall is fine. So we're at 467.2 millimeters. You can also get tricky and count for the gutter, etc. For the sake of this exercise, let's just treat our eaves width as that final distance there, without accounting for our gutters and so on. So that's how we get what our eaves width has to be based on our angle at the height of sun for summer solstice, height in the day. So it's close to midday. I can call it May roughly. So at midday summer solstice, that's our angle of sun. So let's say we were to set our eaves at that. Now I won't go mucking around with this drawing and setting our eaves, but what we'd basically do is move that and bring it over to here to chop our eaves back to 462. Then we've also gotten our angle for winter sun. So there we go. I've just given it 35 degrees. Once again, it's not the actual sun angle, somewhere an approximation of, but I'll leave those inputs to you to determine from your summer and winter solstice and using the sun calculator. But I'll move that one across as well. Let's come up here, and assuming we've moved our eave, that's our sun streaming in through our window there at winter. So just under So if we were to optimize our windows, we could drop that head height just a smidge as well. But this will enable us to determine what the extent of the solar penetration is. We can also, so we'll go distance and then determine that from, let's say, the inside of wall to our sun penetration, and that's 3.176 meters or 3,176 millimeters. And that's pretty much it for determining what our optimum eaves width has to be to protect the windows in the height of summer, and also then what the resultant solar penetration is for winter solstice onto the floor. You can get a little bit more tricky with this. You can get a little bit more nuanced by doing things like determining how much shading that sill will provide in winter. We can go here and get our sill for winter time and cast a shadow there, and then determine the exact amount of slab exposure to the sun there in wintertime. Certainly, if you want to go to that sort of detail in that task, please do so. But just simply getting our summer our exposure for our or protect the eaves width protection of windows in the height of summer, and also our total penetration of sunlight in winter solstice is fine. But that's pretty much it for sun angles. Now it gets a little bit trickier when we go thinking about azimuth as well, because then our sun, once we tip our houses away from that due north, then the sun is coming in at a slightly different angle, and obviously when the sun is at a lower height during the day, it once again starts penetrating in through the windows in summer solstice. That's where programs like Revit are super handy, in that they can map that sun throughout the day, and you can place that building in context with other shading devices and things like that, and get all of your shadows happening to get a real true and accurate reflection. But for the simple calculations for understanding that concept, this type of approach is fine. So that's the concept behind the determining adequate eaves width and resultant solar penetration in wintertime. The other aspect, so that's our windows, and certainly there were some issues with people choosing the glazing as well. Within the Learn page, once again, there is that Your Home guide, which is an excellent guide, but we also have this document here, Orientation for Windows for Best Performance and Economy. So that's a good simple one that was handed out by David during the lecture that's recorded above. But I encourage you for exploring those glazing options. Your Home is a fantastic guide. So next aspect I'll move on to have a bit of a clarification of is the split system air conditioning. So plenty of people have done some fantastic research in terms of finding good air conditioning options, etc. So they're modern split systems, and deciding on what sort of unit to specify. Now you could, there's a whole range of them, and you may land on various different results. That's fine. But the main thing I wanted to point out is, when you find a split system that you think is appropriate, and you're requested to put that information into the spreadsheet, I'm finding that a lot of the power usage figures that are being put into the spreadsheets relate to this, the capacity of the unit. So we've got, this unit comes in a capacity of 2.5 kilowatt, 3.5 kilowatt, or 5 kilowatt. Now, it's very easy to see that and think, okay, well, I've got one unit that uses 2.5 kilowatts per hour, also 2.5 kilowatt hours, so because it runs on 2.5 kilowatts. But this 2.5 kilowatts actually relates to the heating and or cooling power of the unit. So these capacity figures are actually representative of how much heating and cooling the unit can do, not the amount of power, which is not the amount of electricity which is taken to produce that heating or cooling output. So if we want to truly know what these take to run, we have to go and have a look at some more, dig a little bit deeper. So I encourage you, so this one here, tech specs. Now I'm not saying go out and look at Daikin reverse cycle air conditioners by any means. I was just using this as an example. All of your air conditioners will have the technical specifications on them somewhere. And what do we got here? So so technical specifications, there we go, and then we'll want to show full technical specifications. And so in here we have our capacity, our cooling. It provides 2.5 kilowatts of cooling power. That's the influence on the temperature. Or it can produce 3.6 kilowatts of heating or influence on the temperature in a heating fashion. So that's actually the output of the machine. But really efficient machines will actually require less energy to produce those kilowatts of cooling or heating power than what they're actually putting out. So we need to work to run down and then have a look at our power input. So look through the technical specifications. It'll be, there's various different names for it, but like input power, power input energy, etc. But scroll down and have a look for what it actually takes us to run the machine. So here we've got a single phase 220 to 240 volt. And for our cooling, to produce 2.5 kilowatts cooling, we're only having to use 0.42 kilowatts of electricity on this unit. And our heating, we're required, it's to produce that 3.6 kilowatts of heating, it's only using 0.62 kilowatts of energy to run the unit. So that's the common thing that I'm seeing with that with the gizmos task. It's just that misunderstanding that the cooling or heating capacity of these units is not actually directly related to the input energy that's required, particularly on these really efficient systems. So so for those that have struggled with that concept, go in, dig a little bit further, and search out the input energy. Another aspect which I've noticed a little bit on that spreadsheet, not nearly as common as this, is the once again the input energy for the solar hot water service. So in the same, dig around a little bit, look for the input energy on the solar hot water service. And also one thing a couple people have missed is our refrigerators. Typically our refrigerators are expressed as kilowatt hours per annum. So rather than express the power usage of that refrigerator in kilowatts, they're expressed as kilowatt hours per annum, simply because people leave fridges on to run continuously. So that's a more relevant way of measuring or assessing or comparing the refrigerator energy usage. So I hope that's been really helpful to everybody. And certainly if you've got any questions, queries, please email me. and or post things to the forum. Use that hive mind a little bit there to get the input of others that have possibly worked their way through the same issues. So thanks for joining, and I'll see you. Well, I'll be producing another video at some point soon. If there are any aspects that require additional explanation. So thank you.